This is the second lecture from Chapter 14, concerned with kinetics, and this lecture will focus on rate laws, not to be confused with rate. Rate of reaction, as we learned in the first lecture, is equal to the change in concentration of some reactant or product over a certain period of time. You'll learn that rate law is something that allows scientists to predict what a reaction rate will be. So it's more like a mathematical expression. Because we know that the rates of reactions are dependent on concentration and on temperature, the rate law needs to have both of these variables in, which it does, as you'll see. So just to give you a brief introduction to what I mean by rate law, let's look at this generic chemical reaction. So the rate law, and too bad they don't stick in law here. I think that's why some students start thinking it's the same as a rate expression. But is equal to some constant, which you'll learn is the rate constant, that's lowercase k, times the concentrations of the reactants, raised to some power. Now I want to make a really big deal here that these powers, these exponents, have nothing to do with the balanced chemical reaction. These exponents have to be determined experimentally, and we'll talk about that more as we go on. So here's looking at that generic rate law expression again with all the variables defined. The rate constant, lowercase k, has a lot of different factors incorporated in it, which we'll talk later toward the end of the chapter, but temperature is part of the rate constant. Again, these exponents are actually called the order of reaction with respect to each of the reactant concentrations. So in this case, the little a would be the order of the reaction with respect to A, and little b would be the order of the reaction with respect to B. There is something called the overall order of an entire reaction, and that's when you add together all of the exponents. The order of reaction is most commonly 0, 1, or 2. Probably 1 and 2 are most common. I want to tell you on a conceptual level what the order of reaction is before we get into the mathematical description of it. So the order of a reaction, the exponent in the rate law, tells us how sensitive the rate of reaction is to the concentration of that particular reactant. So if you look at a generic rate law, let's just make one up. Let's say that A is our only reactant, and the X is the order of the reaction with respect to A. So this X, this exponent, tells you how sensitive the rate is to changes in the concentration of A. So as you can imagine, the larger the order of reaction, the larger this exponent is, the more sensitive or the more effect this concentration will have on the rate. So if X is 2, if it has an order of 2, that means that every time we double the concentration of A, we're going to quadruple the rate. Conversely, if this exponent X is 0, if it's 0 order, that means it doesn't matter what we do to change the concentration of A, it's not going to change the rate of the reaction. So this is really what you need to take from this. The higher the order of reaction, the more effect the concentration has on the rate of the reaction. So again, as I said, the rate law is an experimental mathematical tool that allows us to predict rates. The orders of reaction, these exponents, have to be determined with experimentally. And once you have the orders of a reaction, you can use a rate law to then calculate the rate constant. Let's take each of the common orders of reaction and discuss what effect that will have on rates. So let's say we're looking at a zero order reaction. So the exponent would be 0. So I'm going to put my generic rate law expression up here again. And let's say that this exponent x is 0. Okay? Hopefully you remember from math that any factor raised to a 0 exponent is equal to 1. So if you have a zero order reaction, what does that mean? That means that the rate is actually equal to the rate constant K, and that changing the concentration of A will have no effect on the rate. Now let's look if the exponent is, or the order of the reaction is first order. So now if you have the same rate law, but instead of having a zero order, you have first order, what does that mean if you double the concentration of A? If you multiply it by 2, then you are also doubling the rate because the exponent is 1. Okay? And 2 raised to the 1 power is simply 2. Now let's look if you have a second order reaction. These are probably the ones, if any, are going to trick you. That's what's going to be. So make sure you understand second order. So second order means that our exponent is a 2. But now, what happens if we change the concentration of A? So instead of concentration A, we have concentration of 2A. What does that do to the rate? Well, 2 squared is what? 4. So by doubling the concentration of A in a second order reaction, we've quadrupled the rate. So we've talked about how the orders of reaction have to be determined experimentally. How do we do that? You actually have a lab in 1212 that will be, it's a method of initial rates. That's what it's called. It's a technique called the method of initial rates, and you essentially do a whole bunch of that chemical reaction over and over, and what you vary is the starting concentration of the reactants each time. And you have all different concentrations of the reactant, which we'll call A at this point, and you're going to change concentration A and then measure the rate and see what the relationship is between the concentration of A and the rate. And that'll allow you to tell what the order of reaction with respect to A is. Now, most chemical reactions have multiple reactants, so 2 is probably a common number of reactants to have. So you would have to find the order of reaction for each reactant, and the order, they're totally independent of one another. So that means that you'd have to run a number of experiments varying the concentration of A, and then a separate number of experiments where you vary the concentration of B. I want to take a couple of minutes at this point to present a different viewpoint of the orders of reaction and how it affects reaction rate. So there are a couple graphs here that I want you to learn how to interpret. So let's look at the one that's concentration versus time. Now, if you remember any type of concentration versus time graph, what is the slope? Okay, the slope is the actual rate of reaction. Remember, rate is defined as change in the concentration over change in time. So let's look if we have a zero order reaction. So looking at the rate law for a zero order, okay, remember we learned in that case rate actually equals the rate constant, and it is independent of the concentration of the reactant. And so you can see here the slope of this line where is zero order remains constant, which means the rate is constant regardless of the concentration. Now let's look for a minute at a first order reaction. That's the middle curve. So we can see, because we have a curved line now, that the rate or the slope is changing over time. It's getting slower and slower. And same thing for a second order reaction. It's a curved line. So what's the primary difference between first order and second order? Well, second order changes more as concentration changes. And you would expect that, right? So if you look at the rate expression, the rate law expression for a first order, have an exponent of 1, right? Versus second order with an exponent of 2, okay? And you would expect the second order, right, to be much more sensitive to changes in concentration. You would expect the rate to increase more as concentration of A increase, more so than a first order. And that's what this graph shows. So now let's take a minute and look at the graph on the right. All right, so here we have plotted the rate on the y-axis and the concentration of reactant on the x-axis. So this is saying, okay, as we change concentration, what's going to happen to rate? Well, zero order, remember, is independent, does not depend on the concentration of reactant, so its rate stays constant. Okay. First order has a direct relationship between concentration and rate. So if you double the concentration, so let's say if we go from 0.2 to 0.4, if we double the concentration, we also double the rate. And finally, second order, if you double the concentration of reactant, you quadruple the rate. So there's a much more steep increase in rate. It's not a direct relationship anymore. It's more exponential. As I said before, this is called the method of initial rates, and it requires several separate experiments, each with a different concentration of reactant. And the important thing to remember is the rate for all of these experiments is measured right in the very beginning of the reaction. You may have remembered in my first lecture me saying it's easier to measure rate of reaction in the very beginning before you have built up much product, because once you begin to build up product, the reverse reaction becomes significant, and then it's quite complicated figuring out what's what. Let's look at a typical table that you would get if you conducted a method of initial rates experiment. So look at the reaction we're doing here between ammonium ion and nitrite ion to give us nitrogen gas and water. So there were 6 separate experiments run, and the concentrations of the reactants, either ammonium or nitrite, were varied. So you look at a typical table like this, and you can find the order of the reaction with respect to ammonium and with respect to nitrite by looking at this data. So what you want to do is you want to pick 2 experiments to compare. So we're going to try to figure out the order with respect to ammonium ion first. So let's compare experiments 1 and 2. I'm comparing those because the concentration of ammonium ion has doubled, and the concentration of the other reactant has remained constant, which is good because we're looking just at ammonium. So when I double the concentration of ammonium, what happens to the rate? Well, the rate also doubles. So what is that relationship when you have a direct relationship? You double the concentration, you double the rate. That means that it is first order with respect to ammonium ion. So now do the same thing for the nitrite ion. You pick 2 trials to compare where the concentration of nitrite has changed, but the concentration of the other reactant remains constant. So to me, it looks like we can compare experiments 4 and 5 because we have doubled the concentration of nitrite. The concentration of the ammonium ion has remained constant. So what has happened to the rate of reaction when we've doubled nitrite? It has also doubled, which means the reaction is also first order with respect to nitrate. So how do we write that in a rate law. Alrighty, so the rate law would be rate equals, always write little k for a rate constant, and they're both first order. When they're first order, it's kind of assumed, so you don't really have to show the exponent, but I just wanted to demonstrate to you that it's there. And so this is the rate law for that reaction. If I were to ask you what is the overall order of reaction, remember you add the exponents together, so the overall order is 2. Here's another example that I want you to practice and see if you can do. Here's a reaction. You have 3 reactants, so you've got to find the order of reaction for all 3. Let's look at the generic rate law expression. Okay, so rate equals some rate constant. You've got to include all of the reactants, and there you have to determine the order for each of these 3. So on the next page is going to be a table of data, and I want at that point I want you to pause the video and see if you can figure out the order of reaction with respect to each of these 3 reactants. All right, so pause the video, try to work it yourself, and I'm going to walk you through it also. All right, so let's take them one at a time. The bromate ion, I want to pick an experimental run that changes the concentration of bromate but keeps the others constant. So I'm going to compare experiment 1 to experiment 2. And the bromate concentration doubles. These stay constant. And the rate doubles. That tells me that it is first order with respect to bromate. Now I'm going to switch and I'm going to look at bromide ion. It's important to pick the right 2 experiments to compare. So in this case, I think I'm going to compare experiment 2 to experiment 3. When I do that, the bromide ion concentration changes by a factor of 2. Bromate stays constant, hydrogen ion stays constant, and the rate of the reaction also increases by a factor of 2. So it is also first order with respect to bromide ion. Now I'm going to look at hydrogen ion. The 2 experiments I'm going to compare for that are, let's see, I'm going to experiment 1, I believe, and experiment 4 doubles the concentration of hydrogen ion, and it's constant for bromide, and it's constant for bromate. So when I double the concentration of hydrogen ion, what happens to the rate? Well, if you divide that, right, 3.2 times 10 to the minus 3, whoops, it's supposed to be a point, over 8 times 10 to the minus 4, you will see that that is a factor of 4. So when I double the concentration, the rate goes up by a factor of 4, which means the order with respect to hydrogen ion is 2. So now let's put all those orders of reaction together into a rate law. The rate law would look like this, right? First order with respect to bromate, first order with respect to bromide, second order with respect to hydrogen ion. The overall order of the reaction is 1 plus 1 plus 2, or 4. It's the overall order. And that's it. Now, one of the things I haven't gone over yet, and I would like to, is I mentioned at the beginning of the lecture that once you have the order with respect to each of the reactants, you can figure out the rate constant. And I'm going to show you how to do that. So once you have the generic expression for the rate law, you can go back to the table of initial rates and plug in values for the rate and the various concentrations, and then rearrange and solve for K. You can pick any of the experiments in the table to use. I usually just pick the first experiment because it's handy. So I'm going to show you on the next page how to do that. All right, so experiment 1 showed that there's a rate of 8 times 10 to the minus 4 molar per second. And when the rate equaled that, the concentration of all of them were 0.1 molar. All right, so the math would be the 8.0 times 10 to the minus 4. I don't know what I'm doing here. There we go. Is K, you multiply 0.1 times itself 4 times, and let's see, or K, I want to keep units in here. There's a reason I want to keep them in here. So when you multiply numbers, you also multiply units, and all these concentrations are molarity. So we have molarity to the 4th for the units on the right side now. All right, so rearranging, K would be 8 times 10 to the minus 4 molarity per second. That's always the units for rate, divided by 0.0001 molarity to the 4th. All right, so what can we cancel? We can cancel one of the molarities, right? So that would give us K equals 8. And what are the units we have left? Well, different ways to express it. 1 over seconds times molarity cubed. Another way to express that would be seconds to the minus 1, molarity to the minus 3. So this is actually very important. Okay, I guarantee this will be on a free response on your next test. It's very important in kinetics to be able to solve for the rate constant using data from the method of initial rates. And it's very tricky for students to learn how to get the units correct, and they are as important or more important than the actual rate constant value. Here is a summary of whether it's first order, second order, or zero order. If you change the concentration by a factor of 2, what happens to the rate? First order is a direct relationship, 1 to 1. Second order is a squared relationship. And zero order concentration has no effect. And here is a final method of initial rates problem for you. And I would really like you to do this totally independent. Here's the chemical reaction of interest. Here's your table of initial rates. And I want you to write the rate law for this reaction. Okay, so I would imagine if you haven't paused it and worked it out, you need to do that first. And also, go ahead and try to solve for the rate constant in this one by yourself too. That's the tricky part. So looking at the nitrogen oxide, I can see that if I look at experiments 1 and 3, I have doubled the concentration of nitrogen monoxide, and the concentration of hydrogen gas has stayed constant in 1 and 3, which is good, so it's not confusing. As you get to more difficult problems, you will not be able to compare to experiments where everything stays constant that you want to stay constant, so they can get trickier. So what has happened to the rate of reaction comparing experiments 1 through 3? It has quadrupled. Okay, so what does that mean? If we double the concentration reactant and the rate has quadrupled, that means it's second order with respect to nitrogen monoxide. Let's check out the order with respect to hydrogen gas. So we want to compare experiments 1 and 2. Concentration of hydrogen gas has doubled. The concentration of nitrogen monoxide remains constant, and the rate doubles. is a one-to-one relationship, direct relationship, so it's first order with respect to hydrogen gas. So if you look at the bottom of the page upside down, we have that, of course, it is second order with respect to nitrogen monoxide, first order with respect to hydrogen gas, and I want you to see if you can solve for K, the rate constant, and get the units correct on it too. When you do enough of these, you'll probably start memorizing units. Notice that the overall order of this reaction is third. So the units for K, the rate constant, for a third order reaction overall are always 1 over molarity squared times seconds. Okay? And so you'll get used to the proper units when you work enough of them. That's it for this lecture.